Hey guys, how are you going? Let's do section 7. We're getting there. I will cover section 7 today, and then our last lesson this week, I will cover 8 and 9. Okay, we're drawing now. We're drawing from using cubic in power form. It's quite straightforward. Let's have a look. Transformation of the cubic function y equals x cubed is very similar to quadratic function. Think about quadratic. Y equals x squared. If we move x, we moved minus a squared plus b, wasn't it? So we moved a and b. The turning point was x squared. Move to a and b. Okay, so they moved it from quadratic form, wasn't it? It is very similar with cubics. Cubic function y equals x cubed. Let's just read this together. A cubic function represented in the point of inflection form shows that transformation require y equals x cubed to produce it. Okay? What does that mean? We only have very limited form here. So we start from y equals x cubed, which, how many solutions here? Only one solution. I mean, in real number, we should have 3, but 2 exists in imaginary number. So and I can say 1x intercept exists. Okay, let's go back to previous class. Yeah. When we have 1, 2, 3 x-intercept or 3 solution, we can have 1, 2, 3 and this looking cubic graph, wasn't it? Positive. And we could have 1 repeated, which means we got 2 solutions or 2 x-intercept. Or we could have only 1 factor or solution, which means only 1 x-intercept. When we have this form, it also x cubed form, because it's all changed from x cubed. You understand? So our graph for x cubed will look like that. Remember, 1, 2, 3 solution, 3 roots, 1, 2, 1, 2, where there's a repeated one, yeah. And when we have only 1, we should have only 1 here. Good. Let's go back here. So from that, I know only 1 x-intercept exists. So this will look like this. Positive, going up, yep, and like that. Only 1. There is point of intersection exists, 0 and 0. That's x cubed. Yeah, and then we can move like x squared, a and b. We also move here h and k. A and b, same thing. And we move h much and k. I will just give you an example. If we move to our point of inflection to think about turning point, it's the same thing. 2 and 3. 2 and 3. Yeah. 2 and 3. So we moved x cube graph to 2, 3. That's probably better, yeah. So it moves to up. So there is your point of inflection from 2 and 3. Previously, point of inflection is 0 and 0. Now, this is x cubed. This is x. Y equals x minus how much? 2. X always have moved, put down opposite sign, plus how much? Y? 3. And cube. Can you see that? Which I explained here. Okay, let's just do one more question with me. Can you do move minus 3 for y axis and 2 x axis? Can you move that from y equals x cubed? Y equals, can you do that in your exercise book? Minus, it's 2, so x minus 2, minus 3, and excellent cube. That's how they look like. And if I draw it, always, when I look at it, cubic here, one solution will look like positive. So this way, point of inflection going down. Sorry, wrong, like this. Point of inflection. Hopefully you get used to drawing that. Okay, that's positive, that's negative. That is positive here, not positive. So I have this. However, that is y equals x cubed. I moved it 2 and minus 3. 2 minus 3. Point of inflection moved to here. I'll go draw it and draw that. I can get x-intercept and y-intercept if I want it. Okay, when y equals 0, x equals 0. But we can leave it there. That is point of inflection 2n minus 3. Are you guys getting it? Hopefully you get used to doing that. Yeah. All right. So the graph of y equals x minus h cubed plus k has a point of inflection h and k, h and k. I keep talking about that. Hopefully you understand the concept now. It's quite straightforward. Just think about quadratic. Okay, and stationary point, done that. They use the stationary point of inflection. When they say stationary, that in that moment, the number doesn't increase or decrease. So its gradient is 0. So, which doesn't mean much for you guys at this point till you learn differentiation. But we'll leave it here, okay? But that's why you can just say point of inflection, but you can use stationary. That actually stands for meaning is here. Your gradient is 0 at that point. Okay, it's just extra information. But I'm happy to keep using point of inflection. Summary of transformation. So it is same as you go back to quadratic. It's very similar. Y equals A. Obviously, A is dilation factor. How much? It is like a gradient. Gradient increase in front of cubic, the highest cube, yeah, highest degree. That always show how that function behave, particularly gradients. Okay, same thing with x equals y equals x, y equals 2x, y equals 3x. That changed it, so the gradient was changing with that same 2x squared, 3x squared. I talked about it. That become narrower. Okay, when x change, y change more, so it become narrower. Same with cubic, x cubed, 2x cubed, 3x cubed. I can increase that, which is I increase a. The graph looks become going upward, which we're gonna have a look next page. And then x translation, yes, y translation here. Don't forget, change your sign for x translation. Okay, we've done that. I already drew that several times using examples, so it should be okay. And move on. Okay, this one, positive, look like that, negative, going down. When x increase, y increase. When x increase, y decrease. That's why that is positive, negative, which means the number in front of x positive, they are negative. You can compare that. Yeah. Can you draw that several times? Positive one, okay, it looks like this. When they have one solution, like this, isolated, or going down, going down, going down. Good. Hopefully you get used to the significant features of the graph of a cubic in power form is point of inflection. We already done it, how they moved it. H and K, point of inflection, done it. And they said after that, so you got the point of inflection. It's like the turning point, very similar. And then you get intercepts, x-intercept and y-intercept there. Good. Yes, it's common. It covers everything unless we actually give the limit for domain and range here. But it will cover whole x and y, which is domain and range. Range is about y, domain is x. Remember that. Okay. For example, I'll just draw here. We had x cubed to produce y equals 5, x plus 2 cubed minus 1. Sketch the graph showing, okay. Sketch the graph, y-intercept and point of inflection. So all we need to do is y-intercept and point of inflection. So from that, I know straight away point of inflection is, or change 2, so it's minus 2, changing, and minus 1. Point of inflection is minus 2, minus 1. And we usually get y-intercept and x-intercept, but in this case, y-intercept when x equals 0, y equals 5. When x equals 0, so 0 plus 2 cubed minus 1. Be careful, this one is not just minus 1. You have to calculate inside. 5, 0 plus 2, 2 cubed minus 1. 5 times 8 minus 1, 40 minus 1, 39. You can go straight away if you want it. So y-intercept when x equals 0, y is 39. So when I draw that, from this, oh wow, x cubed, positive number going up, and then it moves to minus 2, x minus 2, minus 1. So that is point of inflection. And this, yeah. How do I know? I got the shape from here. Positive shape, negative 1, negative. And then, you should draw a bit better, yeah. And y-intercept is 39. We can get x-intercept when y equals 0, but in this case they didn't ask, so I'll leave it away. I got the point of inflection -2, -1, and y-intercept. Done it. Example 1. Okay. Sketch the graph y equals -12 x minus 3 cubed minus 2. Look at that. Ooh, look at the number is what? Positive or negative? Omit? Negative. Negative. Therefore, the graphs look like going up or down? Down. Going down graph. Okay. Dilation is -12. Okay, we get that. So, did I actually cover that? I didn't really talk about this much, wasn't it? Yeah. When dilation increase, let's think about y equals x, and when x increase, y increase twice of x, going up, y equals 3x, y equals 4x, increase that way. It makes sense? Gradient become steeper, okay, when a increase there, yeah, dilation increase. Same things happen here. Cubic x cubed x2 cubed 3 cubed. So that same with the linear, the gradient increase as dilation increase. You understand? And then decrease if that's between 1 and 0. Decrease, 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 and become 0, vary, and then become negative. You understand? Same thing. When negative has a higher dilation number, it will go down more. You understand? So hopefully you understand this graph more. Drops sharper when dilation factor become larger. So start again here. Negative, going down. Yep, point of inflection. Point of inflection is y equals -12 x minus 3 cubed minus 2 minus 3, therefore 3 and minus 2. Point of inflection, I know it's negative, and point of inflection is 3 and minus 2. So 2 numbers here, and all I need is another, yep, x-intercept and y-intercept. When y equals 0, when x equals 0. So let's do y-intercept first. When x equals 0, y equals -12, 0 minus 3, cubed minus 2, and it becomes -12 times -27, -2, -2, minus positive 27, minus 2, 4, to 23. So correct, x is 0 and 23/2. So around 10, 21.5, okay? Sorry, 11.5, yep. So that's, I know, the y-intercept. And x-intercept is when y equals 0 minus half x minus 3 cubed minus 2. So move that minus 2. Eventually, what you want to know is x. So I'll try to isolate x one side times minus 2. So minus 4 x plus 3 cube. I want to get rid of cube minus 4 cube squared cube root x minus 3 and x equals 3 plus cube root minus 4. So when I calculate that, I can say 1, 2. You can estimate without calculator. 1 cube is 1. Okay. 2 cube is 2 times 2 times 2, 8. So 2 is equal to root 8 cubic. Yeah. So when I say 4 is somewhere here, so it's a 1 point something, isn't it? It's minus 1 point something. 3 minus 1 point something. So it's going to be 1 point something. X is going to be around 1 point something. You understand? You got the rough idea there. X and Y. Point of intersection is 3 and 2. 1, 2, 3. It's minus 2 here. And it is negative. And then according to that, the y-intercept is 23 over 2. So around 11, I'll just put here. 23 over 2. And x-intercept is around 1 point something, wasn't it? Yeah. So here, but I can write down just 3 plus cubic square minus 4. And it's a negative, so we'll have basic shape like that. Like this. Point of inflection and going down. So you indicate that x-intercept, y-intercept, and point of inflection. Sounds good. And let's go next. Can you do that example 2 by yourself first? Example 2. I'll pause it and you do it first. It's pretty much the same what we've done so far. Okay, when you've done it, let's have a look. Point of intersection is minus 7 and 1 done. Is that positive? Yes, positive going up, but it is 1 over 4, so it's smaller than 1, isn't it? So this 1 will go down a bit. If there was that is y equals x cubed, it will be more like that, flatter, less increase. Yeah. Y-intercept and x-intercept. Y-intercept when x equals 0, 0, 0. I got 347 over 4. X-intercept, y equals 0. Same thing. Plugged in. 0 equals 1 over 4. X plus 7 cube. Plus 1 and plus 1 move to here, become minus 1. I just did it at once. I'll just write down. And then next. Times 4 times 4. Get rid of cube. How? Cubic root. And then minus 7. So x is cubic root minus 4 minus 7. Good. Minus 4 was around minus 1.5, 1 point something, yeah? So it's going to be minus 8. It just keep going in negative way. So I know 1, hold on, minus 7 and 1. That's point of inflection here. And this is some positive going up, going up, yep. And this one should be smaller than minus 7. Yep, that makes sense. Cubic root minus 4 minus 7. Yep. The point and 0. And y-intercept when x equals 0, y is 347 over 7. I can indicate it. Okay, make sure you're able to draw graph here. You need that skill. Okay, we're done. Can you go, I'll just complete section 7. Go and try that questions. Quite straightforward. All good? Yep, I will complete those two next class. Thanks, guys.